Hello, everyone. Thank you for your presence. My name is Eduardo Morango. I'm here to do this presentation, Effect Systems for Mortals. Okay, so as you can hear, I have a very strong accent and I'm not fluent in English. So please be patient. And if you do not understand what I am trying to say, just interrupt me anytime and I will repeat or maybe ask for some help. Okay? So let's start. Effect systems for mortals. So before I speak about effect systems and a lot of the content of this presentation, let's speak a little bit about intuition first. Effect systems are something related to programming language, to functional programming, to nerd stuff, okay? And usually, this kind of subject is very widening. And to understand that kind of subject very well, we need to go in an abstract path with a lot of nonsensical ideas, okay? And I don't want to do that, okay? I don't want to be formal. I don't want to speak about laws. I don't want to speak about this nerd stuff. I want to speak about concrete stuff. So let's develop intuitions together about the nuance of effect systems, okay? So the point of intuition here is we will think intuition as a mental model of a thing, okay? In your case, effects and effect systems. So uh, before I start to speak about effect systems, I think it's very important to understand why the people are studying, are developing, why people worries about this kind of subject, okay? And one subject very important when we're speaking about development is dev experience. Probably dev experience is what is bounding us today here, okay? We are in the middle of the night speaking about programming. So that subject is very wide too, and I will explore three topics of dev experience. Okay, so let's start talking about expressiveness. Okay, so we like to write programs in a concise way. We don't like to do stuff like Java. I mean, create a lot of phonemic entities and a lot of useless getting setters, or a lot of um, a lot of patterns, meaningless patterns. Okay, so Java is not an expressive language. Okay, and we care about it. We want to develop with correctness. I want to have the compiler as my assistant instead of some kind of unreliable, I don't know, enemy. Okay, so when we are working with JavaScript, usually we have a lot of bad experience in this part of the dev experience. Okay, and we love to speak about performance too, operational performance. Every programmer at some point was passionate about it. We are thinking about happy path. We are thinking about bits. We're thinking about use the last possible cycle of our computers. Okay, and well, for the industry, the performance matters for the industry, of course. But if you think through the point of view of dev experience, we're more worried on how to do concurrent programming, how to do parallel programming in an easy way, okay? So another example of failure in this case is Python, which is an amazing language, but it lacks in some parts of the dev experience, okay? So my point here is that the mainstream language, they just failed, okay? So Java, C++, JavaScript, and a lot of different languages, I don't know, Ruby, they just failed. But fortunately, there are always some weird folks trying to push weird ideas to the mainstream. And because of these folks, that expression, that subject becomes very popular in the last few years, declarative programming, which we usually binds to functional programming. They are not exactly the same, but we can think as the same thing in our context, okay? So we can see Java, we can see JavaScript, Python, a lot of mainstream languages adopting some ideas from declarative programming, from functional programming. And that paradigm favors what to do instead of how to do. So that declarative programming favors one of the many new ends of abstraction, okay? And declarative programming favors composition too. And that's very important because compositions is how our brain works. We get bigger problems, we decompose them, and we start to solve small pieces and compose them again. That's the process for programming, for other areas of engineering, and even, I don't know, in humans studies, okay? So it's very important. So let's explore that point, okay? Composition. Since we're speaking about functional programming, about declarative programming as functional programming, we are speaking about composed functions, okay? And we want to make composition of functions a trivial thing, okay? So we have some properties or some ideas which can help us to make composition trivial. One of those ideas is the idea of total functions, totality, okay? So for every input, I will have a valid output. It's easier to compose functions like that because I'm sure they will not be failing, okay? We love the idea of determinism too, because non-determinism is just a different name for bugs in general, okay? There are some exceptions, but in general, determinism is our ally and non-determinism is some kind of enemy, okay? And of course, we want to compose functions free of side effects. And that's the point. That's the first time we will be speaking about effects or side effects in this talk. It makes sense what I'm saying, folks, until now. Are you managing to understand?
Yeah, perfectly.
Okay. So let me continue. So we have side effects. Side effects mess up the composition, okay? Because usually when we have side effects, we cannot have totality or determinism. They are something which is very easy to exemplify and very hard to define in a single phrase, okay? So before continuing, I just want to say something about effects and side effects, okay? side effects and effects, they are not exactly the same thing, okay? If you speak about effects in some contexts, in some bubbles, if you speak about effects in some contexts, you will not be speaking about side effects. So if you're searching something related to effects in Scala, it's probably different if you're searching about effects in imperative programming language, okay? So they're not the same. It's important to say that, okay? Effects, as I said, it's the same than side effects in the sense they are easy to exemplify and hard to define, okay? So that's the point of meta models. That's the point of intuition, okay? Instead of understand what are side effects, what are effects, let's develop intuitions or a meta model about effects. It's more fragile than abstract nonsensical theory, but it's more practical, okay? And through this intuition, we'll manage to see a lot in our routine as programmers, okay? So let's speak about side effects before we get our first intuition about effects, okay? So we have IO action in Java, okay? So I'm speaking with my user, okay? We have mutability. This snippet is a Scala snippet, okay? We have this we can throw an exception, and this is common in a lot of different languages, okay? And in imperative programming, we have this keyword called void, which usually means some kind of side effects like connect to some database, open or close some file, a lot of stuff like that, okay? And these are side effects, okay? They add events, behaviors, magic, or whatever breaks the totality and or the determinism of a function. So if something can make my function hard to compose, probably is a side effect, okay? And we have effects, okay? So let me show a snippet of Haskell. Here we have a function called head. We will receive a list of A's and return the first A. It will work perfectly if the list is not empty. If the list is empty, what should I do? Usually, the programming language throws a lot of exceptions in this kind of situations. Well, we can just encode, abstract that error in some kind of structure called maybe in Haskell, but it's optional in Scala, optional in Java. They have the counterparts in JavaScript, TypeScript, and a lot of different languages too. And through this abstraction, through this type, this structure, I can avoid a side effect, okay? This function will not explode anymore, okay? So one valid intuition about effects, they are a way to avoid side effects using structure, okay? So let's see another example. Here we have an IO monad of Scala. So we have a lot of stuff happening inside this block, okay? Open and close files, we can connect to database, print some lines, do some logging, a lot of stuff. And in the end, these effects, they are not happening until I call unsafe home sync or unsafe home async, okay? So this time we are suspending effects, okay? So effects are a way to suspend side effects using structure. So sometimes effects tame side effects because they are unavoidable, and sometimes effects avoid side effects from happening. It was the case of head. Through the maybe, we can avoid an exception, okay? And we did not speak about threads, about fibers, about concurrence in general, but with just one line, instead of use room sync, if I use room async, I can manage to use concurrent and parallel programming. So effects encode abstractions too, okay? So I'm handling, I'm avoiding, I'm suspending side effects, and I'm giving behaviors, I'm giving power to the user through effects and through structure again. So that will be our definition of effects in general, okay? Effects are structure. If I have some structure wrapping some block of code, probably I have a candidate to be an effect, okay? And those effects came in different flavors. That's some examples in Haskell, okay? So we have list as an effect. We have tuples, maybe, either, IO, state, reader, and we have a lot of different effects abstracting a lot of different stuff, okay? We have effects outside of the pure functional world, okay, outside of Haskell. We can think in promise as effects. You can find promise in JavaScript, in TypeScript, in Scala, in other languages. We can find observables, which are reactive extensions and exist to almost all the mainstream languages. We have Mono, IO, Zio. If we're going to be strictly formal about following the academic stuff, the people will not like this definition because some of those structures doesn't follow some laws and rules, but we don't care, okay? They are abstraction and they were wrapping code. So they are effects for us. And sometimes we can find something very similar, okay? It's not exactly similar. It's more primitive way to encode some strange behaviors in our signatures, okay? That example is checked exception from Java, okay? So I'm annotating that throws in in the signature of the function, and it's very similar to put some kind of structure, okay? But the throws clause there is part of the language. So it's some kind of primitive structure of the language. And almost all the mainstream languages doesn't do more than that, okay? Some of them have checked exceptions. We can have some different constructions telling something about asynchronous programming, but in general they are very poor, okay? But they are structured, okay? We're encoding behaviors in our signatures, okay? And that's the problem. That is a problem with effects, okay? They don't compose, at least not trivially. Let me show some examples, okay? That's an application using Haskell, okay? We have three different effects. We have IO, we have a either, and we have a maybe, okay? And the point is, when we are wrapping some blocks of code in effects, we handle that blocks through functions. So let's go from the IO to that string value. We have three map functions and we have our two upper function. It works, but it's not an example of dev experience or ergonomics, okay? We can eliminate some values, okay? I can kill some structure using functions like from maybe, but it's the same. Okay, I've eliminated some structure, but I had a hard path to get there. So it works again, but the ergonomics still sucks, okay? And if you think about these constructs of languages as effects, it's the same. We have tricats, but they are not so ergonomic. I mean, I cannot recover one specific step in this block of code. I can do if I put a lot of tricats inside tricats, if I nest a lot of stuff. It's just not ergonomic. And again, effects do not compose trivially. And that's the point. That's the point to effect systems. But before that, there's some possible solutions. Okay, some of them are related to code architecture. Some of them are related to helper functions. And some of them are related to powerful monads. I mean, I want to be either an option, an IO, a write and a state at the same time. It's possible. You can see a lot of this kind of experiments in the Haskell universe, but they're just not ergonomic, okay? And that's the motivation for effect systems, okay? So let me give an intuitive definition, okay? Because effect systems have a lot of formalism, a lot of laws, algebraic stuff, which you don't need if you think in the industry, okay? Effect systems are an ergonomic way to compose effects and give batteries for programmers. So I want to have a way to handle effects. I want a way to handle side effects, a way to do concurrence, a way to do parallelism, to handle errors, and some in the way to embed my business rules, a way to extend that effects. That's the point of effect system. That's the motivation, okay? So they came in different flavors too, okay? So that's not official, okay? It's just a way I use to separate effect systems. So effect systems as primitives. So the checked exceptions of Java is some kind of primitive, but it's not exactly an effect system. It's too poor to be considered an effect system, okay? We have non-primitive, like the IO in Scala, like the observable in a lot of different languages, and we have some effect systems which are questionable if they are primitive or not, okay? So the primitive effect systems, they are usually following the direction of the same direction, okay? And they are usually called of algebraic handlers, okay? So one of the biggest examples is Coca. Coca is a research language which was studying that for more, I think more than 7 or 8 years, okay? We have Unison, probably the most amazing language of the next generation. It's currently in beta, but it's amazing. I will show a few examples of how to handle effects in Unison, okay? And we have Flix. Flix is a new language, a new research language, which becoming near his first version, and it's related to Scala. It's developed in Scala, but use the type system from Haskell, Hindley Milner, and they are trying a lot of different stuff that people usually do not do in the JVM. Okay, we have done primitive like Scala, like Kotlin. Kotlin have libraries for effects which uses the inner capabilities like the coroutines. The most famous is the arrow. If you don't be strict about the formalism, you can think about the reactive extensions for Kotlin as effect systems too. Okay, it's very poor. Okay, but I think we can just consider it. Okay, you have TypeScript too. TypeScript have a lot of promise libraries. Some of them are worried about being functional. Some of them are not worried. I suggest everyone to give a shot to, I think the name of the library, it's Matex Effects. It's amazing. It's based on a new approach to effect systems based on Scala, but it's not primitive. I mean, the folks need to create their own structure, and we need a little bit of discipline to use that libraries correctly. Okay. Oh, it's non-primitive. It's non-primitive structure, and we have the questionable. With the only example, the only example I brought was Haskell, because Haskell doesn't allows to live in some kind of anarchy of side effects. Okay, they have a lot of buildings to handle effects. They have a lot of abstractions related to concurrence, parallelism, error handling, but at the same time, the main component, it just sucks when we're speaking about ergonomics. Okay, so usually when people are working with an effect system in Haskell, is not the full IO. It's some layer of abstraction, some library or framework which use the IO as a base, as foundation, but it's entirely different stuff. Okay, so let's see some examples of effect systems. Okay, let's start with Unison. Okay, that is the signature of an HTTP request in Unison. So you can see that in the signature, we have the braces and the IO and the exception. Basically, we are tracking effects, okay? And it's better than just that. Unison is smart enough to understand, oh, I mean, you are using IO, you are using some kind of exception. So I will infer to you automatically, okay? Different from a lot of languages which are trying to use that ideas, okay? So I've marked this function have an IO and an exception. And probably this function have a different effect too, an HTTP effect, but I'm through this handle with it's not exactly a function, but I'm not sure if it's exactly a statement. Through this primitive handle with, I can eliminate part of the effects, okay? And eventually we will discover the entire point of extensible effect systems is to create custom effects. call them, mark in our signatures, and provide a way to eliminate them, okay? So let's see another example. Of course, Unison allows to create our own effect systems. So in Unison, instead of being called effect systems or algebraic effects or algebraic handlers, we call that concept, we call them abilities, okay? So we can create an ability called abort with that function, aborting, okay? And we have our P in the bottom of the snippet of code. So we have the handle, we have a for plus 2, and we have a call for this aborting. And you can see we don't have the abort in the signature because we're providing a way to this function handle this possible aborting, which is implemented in this other function called abort handler. And of course, if you remove handle and remove with abort handle 0, Unison is capable of inference in the braces. We will be needing a effect or ability called abort, okay? So basically that's the principle, okay? In my opinion, is the smartest way to do algebraic handlers. Colca is very similar. I'm not showing any examples of Colca. There's some caveats, of course, everything have, but in general, we can try different code architectures and we can embed a lot of behaviors in this approach. There's an article of Dan Abramov speaking about a version of this approach for JavaScript. It's called algebraic effects for the rest of us. I recommend you to read about it if you become interested in this approach. Okay, so it's better. It's a better try-cat, which works for asynchronous programming, which works for custom business logic, and a lot of other interesting cases. Okay, we have Flix here. I will show just this snippet here. Okay, so you can see the signature of the main function unit and impure. So basically, Flix is smart enough to understand when I have pure functions and impure functions. So we are speaking about effects more in the sense of side effects, okay? And that's very interesting for the compiler to do a lot of optimizations. But Flix have different goals. Flix is more about tracking effects than standing, okay? Different from Unison, we do the both, okay? I will show a non-primitive effect system. Scala have three very popular effect systems. Two of them are based in Haskell. And one of them is based in these two effect systems with different approaches for encoding. So this guy is some kind of very powerful monad. It's called Zio, and that's a program defined in Zio. As you can read, we have Zio, and we have three blocks. Okay, the first block is where we describe our effects. So we have console, random, and my custom effect. We have a second block describing a custom error. Okay, so this effect system is capable to handle typed errors. And in the third slot, we have the real value, okay? And they follow a principle very similar to Unison, okay? We can create our custom effects. We can just put our business rules. We can create custom business rules, custom interface. We call them traits in Scala, okay? And we can create some implementation to them, okay? And you can just provide. If you look for in my program 2, in the bottom, in the third snippet, in the middle, you can see I can provide all the layers. I forgot to show how to mix, how to define the out layer. It's just the sum of a lot of different effects like console, random, and my custom effect. But the point is, I can mark my functions which needs this kind of effect in their signature, and they can just provide a way to eliminate them. That's the same principle. And by the way, this effect system have a different philosophy if you compare with another monadic effect systems. Okay, he have a lot of combinators, and it's a very concrete piece of engineering, and we can do a lot of stuff. Zero, it's at the same time a either. It's the same time an arrow. It's the same time a lot of very nerd abstractions. And we can just use some combinators and make it simple. So I can eliminate and I can provide a way to eliminate my custom type error. And eventually, when I have an almost clear description of my programs, I can call his runtime system and execute this program. So the point is, when we don't have primitives, usually effect systems are like a programming language, and they have their own compiler, which is called runtime system. It's the same for the other effect systems in Scala, like cats, effect, or Monix. And I'm almost finished. Let's speak a little bit of Haskell. Okay, maybe the uncle of Elm, right? And the Haskell have a lot of different approaches to handle effects and side effects. The most popular and the oldest is the monad transformers plus MTL, which is a library containing a lot of helper functions and a lot of type class to make easier to compose. Okay. Some people follow the principles of free monads, but doesn't matter for us. Okay, in this presentation, they use free, which the next level after free monads, and they are the mainstream of effect systems in Haskell some years ago. Every new effect system was using that concepts, and you have extensible effects. But the point is, they are different. They have some trade-offs, some particularities, but they follow the same principle of I will mark through my signatures the effects and the abstractions I want, and somewhere I will provide a way to eliminate these effects. Okay, so let me show some snippets of Polysemy. Polysemy is my favorite effect system of Haskell. Okay, the others are very similar. I mean, the principle is the same. You can have a reasonable intuition about mark effects and eliminate them eventually. Okay, so it's very similar, okay? I'm creating my custom way to generate an UID. So I can have the signature there. If you look in home UID, we have this R, okay? And we have this same, which the name of the main structure of Polysemy. We have this R containing the effects we'll need to execute this structure, and after that we will always be returning a new same, but without the signature. So required and provide the same principle. Okay, so that's some domain. I did some. I was doing some toy project with Polysemy months ago. So it's basically the same principle. And when we need to execute this domain or service or something like that, the same principle. To run an account domain, I need to have an account repository, a custom effect. I need to have a clock, another custom effect, my own way to generate UIDs, my own way to handle errors, which is different because of the ergonomics of Haskell. And the same principle, to execute a same which needs an account domain, I will send an account domain, a same which needs an account domain, and we'll eliminate them through interpretation. And it's very similar to mainstream language, okay, typed mainstream language. In some place, we will need to get our dependencies, our description, and why everything. So a way to, I need to teach, saying how to run a clock, how to run a YD, how to run an error, okay? In this place here, I'm eliminating everything and turning into a handle. That's the servant API. So basically, this will become the description of some endpoints. So that's my presentation. I was trying to speak about effect systems in a concrete way and intuitive, okay, instead of being very academic. And I think it's that's the point. You describe you want some effect, you provide a way to eliminate this effect, and modern language can infer the effects we need, can infer the purity or impurity of our language, and they allow us to think about the code architecture in different ways, okay? They allow us to think in dependency injection, in testability, and a lot of very important aspects of software development in a more concise and ergonomic way. So that was the presentation. Any questions?
I have one. Yeah, first of all, like, congratulations on the talk. And in Elm, we have something called managed effects, right? Like we have the runtime of Elm. It takes all of your requests for effects called commands. It runs them, but like it's really useful to have this abstraction of like a task, so you can compose effects before you even run them. Like effects are usually just values until you give them to the runtime, and then okay, the runtimes can deal with that. Is that something that is common across the systems? Like, is most of the effects just values that are getting sent to a general, I don't know, like handler of those effects, or usually no, like it's something more like a try catch, like you said, like you're just handling the errors states?
Well, if you go in the nerd way, it's the correct. If you go in the nerd way, the correct answer is both, okay? In the end, and then another possible intuition to effect systems are descriptions, okay? So we are composing a lot of functions, but they are not running. And we will need to run at some time, okay? The responsible component to run this is usually some kind of interpreter. Inside this interpreter, okay, you will have a lot of try-catch, a lot of imperative coding, and a lot of optimizations, okay? I don't know. I don't know the internals of Elm, but some effect systems like Polysemy, they have some way to they have the ARM primitives effects like disembed IO, and the point is, okay, I will give you a set of operations, a set of behaviors, and I will allow you to extend. So that's the approach for extensible effect systems. We have some effect systems like just the IO of Haskell, okay, and they doesn't allow extension. They're just happening. I think I'm not sure how Elm works, okay, but probably inside the interpreter you have a lot of imperative stuff happening. But the point is, usually effect systems are based on laws. They have properties, and they can assure us about his behavior. Okay, so